refraction versus diffraction. Recall that refraction is the bending of light / all EMR as it passes from one medium into another medium. And it could be like Newton was able to refract white light through a glass prism, as we just saw, which causes a rainbow spectrum of the individual wavelengths and colors to appear as the refracted EMR. Notice how the red is refracted or bent the least, and the violet gets refracted or bent the most, just as you guys saw. Refraction is the reason why we see a rainbow after it rains, because the moisture in the air acts like little prisms to disperse the white light. Dispersion is the separation.
Could you go back up to the top?
Yeah. Blah, blah, blah. Dispersion is the separation of EMR into individual wavelengths. So at the top of our sheet, where it says separation of white light, we could also have called that dispersion of white light. So either dispersion or separation. Kind of meaning the same thing in that context. So because white light is made up of a bunch of different wavelengths, each wavelength will have a different angle of refraction. So it will respond differently to the same medium, different angle of refraction. Therefore, each color or wavelength will be bent at different angles, or in other words, separated. Shorter wavelengths, like violet, refract the most, and longer wavelengths, like red, refract the least, just like you put in your paper. Okay? This is why the rainbow always appears in the color order that it does. The spectrum produced by refraction is the exact opposite of the spectrum produced by a diffraction grating / double split screen. Shorter wavelengths like violet diffract the least, and longer wavelengths like red diffract the most. Now I'd left a spot for observations, but we did that. We did that in your sheet, so we can just skip that observation thing. Okay, so that's all we are just comparing those two concepts that we've already reviewed. So now we're going to look at polarization, and this is kind of our last topic. So polarization supports the wave model for EMR. I kind of made a goof here. Also, the idea that EMR is a transverse wave. A polarized wave vibrates in only one plane, i.e. either the electric component or magnetic component of an EMR is eliminated. Non-polarized light can vibrate in all planes. So here, this kind of tries to represent a three-dimensional view of what's going on. So say you have a light coming through. Well, with light, we know that there's an electric field and a magnetic field. So we have fields coming up and out, okay? So it's going this way. And a polarized, film or sheet will only let in one, so either only up and down or sideways. So say this one, since its slits are like up and down, we call it a vertical filter because it only lets the vertical through. So now what's coming out the other end is a vertical line. Okay? Now, if I have a different screen and it's tilted the other way, so it's a horizontal filter, it only lets horizontal through. Well, there's no horizontal left to this light because it's been cut off here. So that's how you, if you have two polarized lenses in front of each other, then you'd block them out. So do you remember doing that? Our first day? You want to try it again? So you can just pass them around. I'll just demo one and then I'll pass this around up to two. So if you hold one up and then hold the other, if you turn it, it will let both in, like if you have it at the right angle, because if you turn it so that, say, they're both vertical filters, then they're both letting some through. But then if you turn it, then it would go black. So you try and pass it around. So it's like, if I have two filters that are the exact same and still have light that goes through, okay, hold it up to a light. You can, yeah.